Section 26 of the Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Chelsea Woods. The Science, History of the Universe, Volume 1. Edited by Francis Rolt Wheeler, Astronomy. Chapter 18, Uranus and Neptune. The discovery of Uranus distinctly represents one of the most important results of modern methods in astronomy. The other planets considered were known from prehistoric times. Even the least conspicuous of them could be observed with the naked eye under favorable conditions. Just as the satellites of Jupiter were the first fruits of telescopic discovery in the heavens, so Uranus was the first planet to be telescopically added to the list, which through the centuries had been known and studied. Its discovery was made on March 13, 1781, by Sir William Herschel, while engaged in the systematic examination of every stellar body visible with his 7-foot reflecting telescope. Herschel states that, in examining the small stars in the neighborhood of H. Gemorium, I perceived one that was visibly larger than the rest. Being struck with its uncommon appearance, I compared it to H. Gemorium and the small star in the quartile between Auriga and Gemini, and finding it much larger than either of them, I expected it to be a comet. Though it appeared as a star of the 6th magnitude, its difference from the other stars was at once appreciated by Herschel, and is evidence of that keenness of sight which was so characteristic of him. Observations of the new body and study of its orbit failed to establish it as a comet. Within 3 or 4 months of its discovery, the conclusion was reached first by Anders Johann Lexell, 1740 to 1784, that it was a new planet which revolved around the Sun in an orbit nearly circular at a distance of about 19 times that of the Earth and nearly double that of Saturn. Herschel's discovery at once won for him a national reputation and royal honors, which he attempted to reciprocate by conferring the name of his royal patron, George III, on the planet, calling it Georgium Sidus. But the name never gained currency outside of England. After a vain attempt to apply Herschel's name to it, the old mythological nomenclature was observed and the new planet became permanently known as Uranus, at the suggestion of Bode, after the father of Saturn and the grandfather of Jupiter. The name means heaven itself, beyond which it was supposed nothing further could be found. Following its discovery by Herschel, with a reflecting telescope 40 feet in length and a 4-foot aperture, came the detection on January 11, 1787, of 2 moons or satellites of Uranus, to which the names Oberon and Titania were subsequently given. Herschel discovered that these moons moved almost at right angles to the ecliptic in a direction contrary to that of all previously known members of the solar system except comets. He suspected the existence of 4 more such satellites, but he was not able to assure himself positively of their existence. In fact, it was only his large telescope and his keen eye that enabled the first 2 moons to be observed. But with the progress of astronomy and the improvement of instruments, other discoveries were bound to come. Within the paths of Oberon and Titania, Ariel and Umbriel were found. October 24, 1851, by William Lassell, a wealthy brewer, who, during his life, devoted himself assiduously and with great success to astronomy, especially telescopic observation. These satellites, although not easily visible in a telescope on account of their distance, are much larger than the satellites of Mars, or in fact many of the planetoids. It is estimated that their diameters are between 500 and 1,000 miles. Oberon, which is distant from the planet 365,000 miles, has a period of rotation of 13.5 days. Titania, the largest and brightest, distant 273,000 miles, has a period of 8.7 days. Umbriel, distant 167,000 miles, has a period of 4.1 days. And Ariel, distant 120,000 miles, has a period of 2.5 days. These satellites all move in the same plane, which is inclined about 98 degrees to the plane of the planet's orbit. These satellites revolve in a retrograde direction. The surface markings observed on Uranus by many astronomers have been vague and transitory, so that any determination of the period of rotation is but approximate. Nevertheless, a period of 10 or 12 hours has been indicated. It is said that the plane of the equator is inclined something like 10 to 30 degrees to the plane of the orbit of the satellite. The disk of the planet shows a flattening at the poles so that it has an elliptical section. The appearance of Uranus to the naked eye is that of a small star of about the 6th magnitude. It was on this account that a high-powered telescope was required to differentiate it from the myriad of other stars of this size to establish it as a planet. It is so far away that there is but little change in its position, whether it is in opposition or quadrature. Measuring the disk, which appears in the telescope to be of a sea-green color, the diameter of the planet is found to be about 32,000 miles, or 4 times as great as that of the Earth, which would give it a volume 64 times greater. But, like other distant planets, Uranus is composed of lighter materials, so that while 64 times as large, its mass is but 15 times that of the Earth. Or, in other words, Uranus would compare with the Earth in about the same proportion as regards volumes as does the Moon with the Earth. The elliptical orbit in which Uranus moves at a mean distance from the Sun of nearly 1,800,000,000 miles requires 84 years for its passage, and the diameter of this orbit is 3,600,000,000 miles. The orbit is slightly less eccentric than that of Jupiter and amounts to 83 million miles, while the periodic time of the planet is 84 years and its synodic period 369 days and 16 hours. It moves with an orbital velocity of 4 1/3 miles per second. In the first half-century after its discovery, Uranus gave astronomers considerable trouble, as observations showed that it was not following exactly its computed path and that it deviated by a substantial amount. By 1830, Bessel suggested that the discrepancies in the observed and calculated orbits might be due to an unknown planet, then more distant from the Sun than Uranus, and such was found to be the case. As Uranus was the triumph of telescopic discovery, so Neptune represents one of the greatest achievements of mathematical astronomy. In fact, when the French astronomer Leverrier at Paris wrote to Gall at Berlin substantially as follows: "Direct your telescope to a point on the ecliptic in the constellation of Aquarius in the longitude 326 degrees, and you will find within a degree of that place a new planet looking like a star of about the 9th magnitude and having a perceptible disk." The German astronomer, within 30 minutes after he had begun his search, on the night of September 23, 1846, was able to find the new planet, but 52 feet distant from the point indicated by Leverrier. The discovery of Neptune came, as had been suggested, from discrepancies observed in the path of Uranus, which oftentimes were almost so marked as to be observed without the aid of a telescope. As an explanation of the disturbance, an unknown exterior body was suggested, which was not only plausible, but so obvious that several astronomers were devising mathematical plans of campaign for its discovery. A young graduate of Cambridge University, John Couch Adams, 1819 to 1892, who had distinguished himself in mathematical work, assiduously addressed himself to the problem, and in 1845 sent to the Astronomer Royal at Greenwich numerical estimates of the elements and mass of the unknown planet, together with an indication of its actual place in the heavens. Unfortunately, Adams' work, for various reasons, was not taken up by the government astronomers, and in the meantime, Urbain Jean-Joseph Leverrier, 1811 to 1877, as a result of the study of the stability of the solar system, especially of the Uranian difficulty, to which his attention had been directed in 1845 by Arago, announced before the French Academy that only an exterior planet could produce the observed effects. Such an announcement aroused astronomers to a point of expectancy. And in fact, as Sir John Herschel declared to the British Association regarding the hypothetical new planet, we see it as Columbus saw America from the coast of Spain. In less than 2 weeks from the time of this utterance, the message quoted was sent to Gall at Berlin. Within a week, Neptune was also observed in England, where delays lost the honor of priority for Adams. Once the existence of the new planet was established, a few weeks' observation made possible the computation of its orbit and its identification with what had been considered a fixed star. Neptune supplied the exception which proved the rule in the case of Bode's law, discussed in the chapter on planetoids, for its mean distance from the Sun was 2,800,000,000 miles instead of 3,600,000,000, as would be required under the terms of the law. Furthermore, Neptune has an orbit with an eccentricity of only 9 octillionths, so that its path is more nearly circular than that of any other member of the solar system except Mercury. But so large is its orbit that the small eccentricity makes a variation of over 50 million miles in the distance of the planet from the Sun at different parts of its orbit. Moving with an orbital velocity of about 3 1/3 miles a second, it requires 164 years for its journey around the Sun. Neptune has but one satellite, which Lassell found in 1846, within a month of the original discovery of the planet. Its distance is about 221,500 miles, and its period of revolution is 5 days and 21 hours. It is a small body, about 2,000 miles in diameter, or about the size of the Earth's moon, and it moves backward just as the satellites of Uranus, in an orbit that is inclined 145 degrees to that of the planet. Like Uranus, Neptune varies little, as its distance is so great that any variation by change in the position of the planet would not affect its appearance on the Earth. Its diameter is estimated at about 35,000 miles, which would give a volume of 85 times that of the Earth, or, according to Professor T.J.J., CUSN, 27,190 miles. But, as is also the case with Uranus, it is much lighter than the Earth. As its density is probably about 0.20, its mass, which astronomers compute from the motion of its satellite, is about 17 times that of the Earth. On account of its great distance, it receives from the Sun about 1/906th the amount of heat that falls upon the Earth. If its capacity for absorbing and retaining heat are the same, the theoretical temperature would be about 360 degrees Fahrenheit, 220 degrees Celsius, or between the temperature of liquid air and the boiling point of hydrogen, a temperature so cold that on the Earth, complex methods to produce it have to be adopted in a physical laboratory. Nevertheless, the amount of light received from the Sun is not insignificant, and the noonday illumination of the planet would be some 700 times that of the brightest moonlight. If the Sun were placed at Neptune, its light would equal that of 687 full moons. No surface markings have yet been seen on Neptune. Consequently, astronomers are unable to determine its rate of rotation by direct observation, but from various intricate processes, Neptune is believed to have a slower rotation than Jupiter or Saturn. End of section 26.